Hello, my name is Brooke Taylor. Suppose we want to create a function that will approximate the value of another function when it is centered around a certain value. Why? Well, the short answer is that it is useful in computer science, engineering, computational science, physics, and almost any field in which complicated functions are used and are in need of being simplified. Also, sometimes we only have enough information to make approximations anyway. So what's the simplest form of a function? A polynomial, of course. Surprise, it was me the whole time. Okay, so let me talk about what just happened, other than the fact that you saw a picture of a guy with amazing hair. Wish I had a wig that would demonstrate it. This is the function e to the x over 2, which is the next example in the next video, but I just want to give you an overview of what's about to happen, and here's what's about to happen. We are going to take tangent lines and go to the extreme. So, tangent lines approximate a function at a point by doing two things. They are able to say, I know the value of the function at that point. For example, the value of the function e to the x over 2, where x equals 0, is 1. Okay? So, 1. Right there. Right now, I have a function. It's a really lame function, but it is the function y equals 1. It is a terrible approximation. So tangent lines do two things. Tangent lines have the exact same y value at a given point. In our situation, we are dealing with the point x equals 0. This thing is going to be centered at 0. I say centered because if it was not centered, then we would say it's off center. But technically that is going to be the center of our approximation. So let's take this back to 0. No, get it just right, get it just right, get it right. There we go, perfect. So tangent lines, let's start all over. Tangent lines have the same y value, and they also have the same slope. And because they have the same slope, you can ignore some of the guts of what's happening here. Boom. Now we have a tangent line. In this case, it's going to have a slope of 1/2, which makes sense, because the derivative of e to the x is e to the x. The derivative of e to the x over 2 would be 1/2 e to the x over 2. Plug in a 0, you get a 1/2. So not only do we have the same y value, we also have the same value of the first derivative. So we have the same y value, meaning the 0th derivative, and we also have the same value of the first derivative. Maybe we can get an even better approximation if we have the same value of the second derivative there. So, good approximation? Yeah, pretty good. Let's zoom in. Yeah, pretty good, but you know, it has its flaws. Not the best approximation. Let's take this up to the second derivative. Don't panic about what all is going on over here. Do not look behind the curtain. But this is just a way that it's been programmed to where you'll be able to see as we get higher and higher in the degree of this polynomial. You'll know what I mean in the next video. But as we get higher and higher in the degree of this polynomial, we're going to get a better and better approximation. So previously, on the last, when we last left our hero, we started with this terrible approximation. We went to a tangent line, a mediocre approximation. Then we went to a tangent parabola, I guess, and then we ended up with a much better approximation. Notice how the red and the green are getting closer together. So let me go back to a standard view, and it has its flaws, but around x equals 0, where it's centered, it's pretty good, right? All right, so let's keep going. Tangent cubic function, I guess. No one calls it that, but we're going to do that. So tangent constant, clearly not a tangent. Tangent line, tangent parabola, misusing the word tangent here. Cubic function, quartic. And as I scroll through, I can only go up to 7 on the way this one's programmed. But as I scroll through, notice that it becomes a better and better approximation. However, as you look at it, you're probably watching this tail wag over here. But as you see this tail wag, notice that as it does, it overlaps more and more. Now, it's not overlapping perfectly, but it's getting to be a better and better approximation. So here's the deal. Next video, we're going to walk through an example of this in which we're going to do tangent line, but then we take it a step further with the second derivative and third derivative and fourth derivative to get even better approximations. Now, why do we do this? Glad you asked. The reason we do this, and this was something that Brooke Taylor said at the beginning of the video, the reason we do this is to save computational power. Now, I realize in the technology that we have the ability to do all kinds of things computationally, but you'll hear me say this in a later video that I've actually already recorded in this lesson. Sometimes it's going to be cheaper if you use cheaper computers, and so you don't need all this supercomputer power, and you can just use approximations when you're centered around a certain value, and that's going to be clearly sufficient for what you're doing. It saves computational power, it saves computational ease. It's a fantastic way of doing things when you don't know the actual function. Sometimes you know the actual function, sometimes you don't, but you just have enough data to where you have no choice but to build approximations. So that is an intro to Taylor polynomials. Here we go. It starts with a constant, it goes up to a tangent line, then a polynomial, then a parabola, cubic, and it just keeps going. And the more we do, the better the approximation gets. If I could take this all the way to an infinite number of terms, this tail would keep on wagging and it would eventually overlap over the entire thing. It is absolutely beautiful. I hope you're as excited as I am. Let's do an example.